Hello students, in this lecture we will see our next topic, that is logic level. Under this topic we will see gate, reorganization, signal gating along with logic encoding. So I am taking this topic from the book Practical Low Power Digital VLSI Design by Gary Yep. So before starting this topic, first we have to understand that what is uh, what is logic and why we introduce this topic. Why we introduce this topic here? We already know that to implement low power circuit, the main criteria is to minimize the power dissipation, to minimize the switching, to minimize the input frequency, etc. So while we are designing the circuit, so at that time the logic design is the basic of VLSI chip design. The logic design is the basic of VLSI chip design. Okay, and when we use some HDL languages means such as VHDL language, such as Verilog language, etc. So when we use this VHDL language in any digital circuitry for the programming, at that time also there are many techniques. At the time there are many techniques that can be used by the designers to minimize the power, to reduce the power. Okay, so in logic level the power optimization most commonly used technique is reduction of switching activity. Okay, it means that if we want to reduce the power, then in logical level what we can do, we can do this by using the reduction of switching activities. Now we have to discuss what is the mean of switching activities. We have to know that what is the mean of switching activities. Switching activity, we know that power dissipation is basically divided into two types. First one is the static power dissipation, and the second one is the dynamic power dissipation. Okay, first one is the static power dissipation and the second one is the dynamic power dissipation. Also we know that switching power or static power is again dynamic power dissipation is again divided into two types. One is known as switching power and one is known as short circuit power. Now how switching power is dissipated, how switching power generates, switching power dissipation is generated due to the charging and discharging of capacitance that is connected in the load side of the transistor, load side of the output. Okay, it means that when the capacitor is charged, when the capacitor is discharged, at that time because of this switching activity some power will be dissipated, and because of this power because of this power dissipation, the performance of the circuit reduces. Okay, and the second factor is short circuit. Due to short circuit current, the power is generated, power is dissipated, that is known as short circuit power. But this short circuit power is approx 10% of switching power. Okay, that's why in the case of calculation of dynamic power we always consider the switching power, because switching power is because short circuit power is almost the 10% of switching power. Okay, so basically the role of switching power is significant in the case of dynamic power. Okay, so it means that if we reduce the switching, in the case of logic, we are discussing logic here. Okay, so if we reduce the switching in the case of logic generation, then automatically we can say if switching is reduces, then automatically the power dissipation, the dynamic power dissipation will reduces. Okay, so So that how can we reduce this switching activity? How can we reduce this switching activity? Okay, so we can reduce these switching activities by using the logic organization. Okay, that all we study in our today's lecture. So when we reduce the switching activity, so automatically the power that is dissipated will be reduced. Okay, so now we will see how to manage this how to manage this dissipation. So for manage this logic reorganization, so to manage this power dissipation, um, by using the logic analysis, we can do this by using the gate organization. It means that gate organization is under the category of logic level. Okay, it means that if we want to reduce the power dissipation, if we want to reduce the switching power dissipation by using some logic, so at that time we can move towards the gate organization, or we can move towards the switching activity, or we can move towards the some encoding scheme. Okay, so how can we reduces the power in the by using the logic activity? There are the three different ways. First one is the by using the gate organization, second one is the by using switching by using signal gating, and the third one is by using the encoding. Okay, these are the methods in the logic level. By using all these methods we can reduce the switching, and when we reduce the switching, so automatically the power dissipation will be reduced. Okay, so first we will discuss what is the mean of gate organization. Okay, reorganization means a transfer of structure, reorganization of structure, we can say. Reorganization means reform the structure again, form the structure again, we can say. Okay, so reorganization is not limited to transistor level only. Transistor level reorganization in transistor level we already discussed. It means that suppose I have made a transistor, I have made a circuit by using the transistor only. So at that time some power will be dissipated. So if we want to reduce the power dissipation, so we will reform the transistor structure. So this one is known as transistor reorganization. Okay, but if we want to reduce the power dissipation in the gate level, so we can say it gate reorganization. Okay, so what is it means? It means that we need to change the structure of gate. We need to change the structure of gate. Okay, so if we change the structure of gate to reduce the switching activity, to reduce the power dissipation, it will under the category of gate reorganization. Okay, all these are mentioned in the first paragraph here. Okay, so by using gate reorganization, we can increase the power of the we can improve the power of the circuit. Okay, because we can improve the performance of the circuit. We can improve the performance of the circuit because in any digital circuit the performance is directly related with power, area and delay. So if we reduce the power, if we reduce the area, if we reduce the delay, so automatically we can say we are increasing the performance of the circuit. Okay, now the technology mapping that is mentioned here, technology mapping. The technology mapping is very similar to the gate reorganization, except that the original network is expressed in a generic form such as two input NAND gate only. Okay, so most reorganization tasks today are performed by automated software. Now what is it means? It means that suppose I have made a circuit by using some gate, and I found that some power dissipation will be there. So, power dissipation is there. So what we can do, we can change the its structure. We can change the number of gate. We can change the connection between one gate to another gate. It means that we need to reorder our gate combination. It is known as gate reorganization. Okay, so what is our main task? Our main aim is to reduce the power dissipation. Okay, so for this, various automated software are presented now. By using that, we can reduce the we can change the gate structure automatically. Okay, we just need to feed the gate structure there, and found various gate reorganization, and find various gate structure through which we can analyze how much power is dissipation in every case. Okay, so accordingly we will summarize which one is beneficial for our task. Okay, so commercially and academically. So commercially and academically, we use some logic synthesis tool that automatically done reorganization for power and in terms of power and area. Okay, so in this case, in gate reorganization, we can do gate reorganization by using local restructuring. We can do this gate reorganization by using local restructuring. What is the mean of local restructuring? Local restructuring means the change the physical path, change the physical dimension of the gate. It means that we can change the number of gate, we can change the path, we can add some path. So by using this local restructuring, we can reorganize the gate. Okay, so in the case of local restructuring, several transformation operations are there. We will discuss it, we will discuss every transformation operation later. Now the transformation operation means change of one structure to another structure. It's known as transformation. Now the transformation operation does that drastically changes the delay and power of the circuit, has no practical value. Okay, because we need to change the circuit, we need to change the circuit according to our requirement, according to our according to convenience of the circuit. Okay, so so that most of the logic restructuring techniques are local restructuring to transform one network to another. Okay, so this affects very few of gate. So by using this local restructuring, only few gates, only the combination of few gates are affected, only the combination of some wires are affected, and everything in the structure will be same. Only some wires, only some gates are restructured, and nothing will be changed. Okay, so by using some reduction of wire, by using some minimization of one or two gate, we can reduce the power according to our requirement. Okay, so after this gate reorganization procedure is applied, a series of local transformation to the network. So there are some techniques given here, such as we can use combine several gate into a single gate. We can combine several gate into in fact we can say we are merging here. Okay, so by combining several gate into a single gate. Second one is the decompose a single gate into several gate, and the third part is the duplicate a gate and redistribute its output connection. Fourth one is the delete a wire. Fifth one is the add a wire, and the last one is eliminate unconnected gates. all these all these operations of gate restructuring, gate transformation, is represented in the represented by using some gate structure here, such as the first combination that is mentioned here. This first combination represent the first operation, that is combine several gate into a single gate. So we can say we are doing a combination. Okay, we are eliminating this extra wire, we are eliminating this extra wire. Okay, we are eliminating this extra wire. by combining one gate to another gate. So when we are doing this combined operation, so by using, we are reducing the wires. So when we are reducing the wires, so automatically the propagation delay where reduces, and also we can say the power dissipation will reduce it. Now decompose decompose is just a reverse operation of combine. So according to circuit requirement, we can do combine operation or decombine operation. Okay, so this one is the combine, and decompose is just a reverse operation of combine. Now this one is the duplicate. Here you can say we are getting a we are getting two input signal to we are providing two input signal to the NAND gate, and the output of NAND gate is provided as an input to some other gates. So in the duplicate, what we can do, we can use two NAND gate instead of using one gate. So when we are using the two gate instead of using one gate, so here two gates are used. So this operation is known as duplicate. This operation is known as duplicate. So this one is also operation that we are using in the gate restructuring. Okay, here you can say this a here this one is a, this one is b, this one is c, this one is a, this one is b, this one is c. This we can delete any wire. If we delete this wire a, so this one is the output combination. This one is the fourth delete a wire. If we can delete the wire, if it is possible, is there is no significance of this input terminal, if there is no significance of this signal, this input, so we can eliminate this wire in our next structure, reform structure. Also there is some add wire. Here you can see this one is the structure, and we are taking an input and providing it as such as mentioned here. So if we reform this structure as this structure, so you can check it out. The output of this one and the output of this one is same. Okay, so by using these all operation, we are just doing a gate reform, we are just using a gate transformation, and by using that we can reduce the logical switching, we can reduce the power dissipation. Okay, each operation have a significant each operation have some advantages that all is mentioned here, such as the combined operation can be used to hide the high frequency node. Okay, so same as the decombines or the duplication operation helps to separate the critical path. Same as the delete wire operation reduce the circuit size. The add operator helps to provide the intermediate circuit that may eventually lead to a better one. Okay, so all these gate transformation operation have significant advantage, that all are mentioned here. Okay, now the next one is signal gating. Okay, in the first part, what we are doing a gate reorganization. In that we change the in which we change the number of wires, in which we change the number of gates, and form a new structure, so that we can minimize the power. Now here we are taking the second method through which we can reduce the switching, because in logic level we need to minimize the switching only. Okay, now how can we minimize the switching? In logic level? How can we minimize the switching in logic level? We can minimize this switching by sometime we can minimize the switching by using some signal gating. Now what is the mean of signal gating? Signal gating means we are doing some masking of unwanted we are doing some masking to prevent unwanted switching. How can we reduce this masking? How can we reduce this switching? We can reduce this switching um, if we mask the signal, such as the input signal is not provided as the output of one gate is not provided as the input of another gate. If we do some interruption between them, So by using that, by using, if we restrict the signal from one gate, so it is not possible. If we reduce the, if we restrict the signal, such as this signal is not provided as an input to the another gate, so by using this, we can reduce the switching, we can reduce the unwanted switching, and how we can restrict this signal. So for restriction of this signal, we can add some and or gate combination, and gate or gate combination, or sometimes in some circuit, some latches and flip-flops can be used to block the propagation, to block the signal. Okay. Sometimes some transmission gates are used for the same purpose, or we can say, for making some interruption between input and output. Okay. So these are some ways, there are some ways through which we can block the signal, okay. So by using this AND gate, by using some this tri-state buffer, by using this latches, by using this transmission gate, we can block the signal. If we block the unwanted signal, such as if we block a unwanted signal for the restriction of switching, so we know that if we reduce the switching, so automatically the power dissipation will reduce. Okay. So you can understand, signal gating means, signal gating is a way to block unwanted input signal to restrict the unwanted switching. That's it. Okay. And for this gate switching, we can use these all operators, these all gates, such as AND gate, OR gate, buffers, and buffers, or flip-flops, latches, transmission gates, etc. Okay. In short, for blocking of unwanted signal, you are using this, and if you're using this, unwanted input signal is not provided in the another gate, and it reduces the switching. Okay. Now the next one is the logic encoding. We know that encoding means, what is the mean of encoding? And encoding means conversion of one logic into another logic. If we change a one code into another code, so this method is known as encoding. Okay. So if we do encoding, so by using encoding, we also can reduce the switching. How it is possible? We know that in the digital circuitry, input is the combination of 0 and 1 only. It means that if we provide the 0 1 0 1, it means that input is switched in every time. When we provide 0, so there is a constant input, but when we provide 1, so input is switched from 0 to 1. When we provide again 0, so input is again switched to 1 to 0, and when we are providing again 1, so input is again switched to 0 to 1. Okay. So this switching is also occur in the output side. Okay. So if we reduce this switching, so if we reduce the switching, so we can so the input that is provided in the circuit, if we reduce this switching, so definitely for this for this purpose, we need some encoding circuitry there. Okay. So here we are using a logical encoding circuitry. How it works? To understand this topic, first we have to understand the two types of code. One is binary code, and the second one is the gray code. Binary code is the weighted code. Weighted code means each bit have some weight. Okay. So when we are if we want to represent a 1 number to 10 number into binary code, so its representation will be 0001 001 0011 0100 0101 0110. All these are represented here. Okay. Suppose in the first time, if the input is 000, so there is no switching. Okay. But if the next input is 001, so one input is changed, because so we can say one switching is occur here. So if now the present input is that, now when next input comes, so how many bits are toggled? 2 bits are toggled. two bits are switched. Now if the input is switched from this one to this one, so how many bits are toggled? So one bits are toggled. So you can see here 1 2 1 2 3 1 2 1. These all are the switching, these all are the toggles. So to eliminate this switching, because we know that if switching occurs, so definitely switching power generation will occur, and because of this switching power dynamic power dissipation occur. So we can reduce this binary, we can convert this binary code into gray code. So if we convert this binary code into gray code, so these all are its respective conversion. So if we convert 0 1 1, so its conversion, the gray code conversion is 0 1 0. If we convert 1 0 0, so its gray code conversion in 1 1 0. 101, its gray code conversion will be 111. 110, its gray code conversion will be 101, and 111, its gray code conversion is 100. Now if input is 000 at in starting, there is no toggle, so the first bit will be 0 because here no toggle is there. Now the next one is 001. If this if the next input is 001, so we can say only one bit is changed, so the toggle is 1. Now if the input is 011, so only the second bit is changed, so only one bit toggle is there. So here you can see only one bit is toggled. It means that only one bit is switched and every time. So it is very advantageous as compared to binary code. So in encoding circuitry, what we will do? So in logic encoding, what will we do? We can directly use the gray code instead of using binary code. Okay, here some number of switching is here. In the case of counter, the transition is represented by, if in the case of counter, if you are using a binary code, so number of transition is represented by this mathematical equation, and if you are using a gray code, so it's a its a transition is represented by this formula. Okay, in the case of counter. Okay, so you can put value of n as 1 2 3 4 5 6, and you will get the number of toggle that is found here. Okay, so in each case you can see the number of toggles, the number of switching in the in the gray code is less as compared to the binary code. So it is very advantageous in the digital circuitry to use the gray code instead of using binary code. So if we use the binary gray code, so we can reduce the switching. Okay, now how can we use this? We can for this purpose we can use this bus invert structure. Okay, first method is this: we can use the gray code instead of using binary code. Now the second method is we can use the bus invert encoding. The structure for bus invert encoding is represented here. You can understand this structure by using a simple example. Okay, such as if the input is 000, if the input is of 4 bit 0000, and the next input is 1110, so you can say 3 bit, you can see 3 bit toggle is there, 3 bit toggle is there. And because of this switching, definitely the switching power is generated, switching current is generated, and because of this switching current, switching power will be generated. Okay, so what we will do, we can instead of using this 1110, we can do its complement. If we are using its complement, so what is the complement of 1110? Its complement is 000 and 1. It is represented here. So instead of using this as second input, we are using this as second input. So if you are using this as second input, so how many bits are toggled here, how many bits are switched here? Only one bit is switched, so we are reducing the power. Okay, but the input is this one, but the input is 1110. So at that time sub polarity, so at that time we are using the input 0001 in the transmitter side, but in the same case we are sending a polarity signal. Polarity is decision logic in the receiver side. It suggests the receiver that the input that is received now is inverted. So when we when the input is received as 0001, so the receiver invert it as, the receiver take a complement of this input as 1110 and accept this input. Okay, so instead of sending this 1110, I am sending 0001, and along with this 0001 we are sending one another polarity signal to the receiver, and when receiver getting this polarity signal, so it know that the received signal is inverted, and receiver again take the complement of this signal and find the correct signal. Okay, so this one is the method to reduce the switching. Okay, so this one is the known as the this one is the architecture of bus invert encoding. Okay, so these are the methods, these are the three methods, these are the three methods under the category of logic level. So by using this logic level we can reduce the switching, and if we reduce the switching, so automatically the switching power dissipation will be reduced. Okay, switching power dissipation is under the category of dynamic power, so if switching power reduces, dynamic power is reduces. Okay, so uh, okay, in so this is all from my side. In next lecture we will discuss some other topic, um, state machine encoding and pre-computation logic. Okay, thank you so much.